It's like saying I first died, like I'm trying to drown that.
You didn't die, get over it.
Exactly.
All right, if you guys can turn to page 5. So today we're going to be talking about how to graph and interpret F prime graphs. This is an important topic. On the AP exam, they love to provide a derivative graph and ask students about the behavior of the original graph. And we'll get a chance to practice that today, tomorrow, and a little bit on Monday as well. Okay. So page 5. Okay, so we're going to start off with something that feels a little bit more straightforward, and then we'll kind of circle back to how to work from a derivative graph, or how to start from a derivative graph. Okay, this is we're going to start off with the original function here. Okay, so whatever you see is what you expect in terms of relative max, relative min, increase, decrease. Okay, so everything that you see is very straightforward. Okay, so we're going to make a sign line for our slope, and then we'll deal with the concavity a little bit later. Okay, so first, let's look at our function graph, and let's create a slope sign line. What we're going to do is, when we create our slope sign line, this is going to eventually act as the bridge to our derivative graph. Okay, but we'll create our slope sign line here. I'll call this slope sign line. But before we do that, well, yeah, so we're going to identify our critical points, which is our peaks and valleys. So what values can we put onto our slope sign line to begin with? Where do you see your peaks and valleys here for our graph? Okay, good. -3. Where else? Yeah, 1. And yeah, I meant for this to be a -1. I know it looks a little bit off here, but let's say -3, -1, and 1. Okay, so we'll go ahead and put those onto our slope sign line. Okay, now let's talk about the slope, right? What slope do you see to the left of -3? Positive slope. So we'll say positive slope here. Okay. Between -3 and -1, negative slope. Okay. Between -1 and 1, positive slope. And then to the right of 1, negative slope, right? So you see how the arrows are going to match the behavior and movement of your original graph. So now what we're going to do is we're going to create something called the derivative graph. Okay, so call this F prime. Now, what makes a derivative graph different is really the y-axis. Okay, the y-axis is now going to represent something different from the original graph. So if you look at the original graph, the y-axis represents the location, okay, or the height of graph, right? And so what you see is what you get. You know, this is, let's say this is a y value of 3, so that's the height of 3. Right, the highest point is your relative max, lowest is your relative min. Okay, so we know how to look at a function graph and be able to interpret that. Now, a derivative graph is now going to represent something about the original graph, but the y-axis is not going to give us the location of the graph. It's going to now represent the slope value of the original graph. The slope value of the original graph. So, you know, if our y-axis is defined differently, then we shouldn't expect the two graphs to look the same. Okay? But they are going to be very much related. Okay, so now let's talk about slope values of the original graph. What's special about these peaks and valleys? They all have slope of what? 0. Okay, so if I want slope 0, then it's going to have to be on the x-axis, right? Because that's when y is 0. Okay. So let's go ahead and label that to help us remember. Anything that has a slope 0 needs to live on the x-axis, because now our y-axis doesn't represent location anymore, it represents the slope. We say slope here is 0, slope here is 0, and slope here is 0. Okay. So what are those x values going to be? Okay, -3, -1, and 1. So go ahead and plot those points. And this is going to be really helpful because we know that our derivative graph will have to go through those points. Okay, we've already found them. Okay. And okay, so now we want to talk about what does this region represent and what does this region represent. So anything above the x-axis is when slope is what? Positive. Okay, so we're going to have a little diagram or a little something to kind of help us remind ourselves what we're dealing with here. So anything above the x-axis is going to be a positive slope. We're going to match this symbol with the symbol that we see on our slope sign line. Okay. So anything below the x-axis is going to represent where my original graph is going to experience what? Negative slope. All right. Good. So what we're going to do is we're going to try to sketch our graph based off of just our slope sign line. Okay, we're not going to look at this anymore. We're just going to rely on this to help us create the picture of our derivative graph. Okay, so what do we want to the left of -3? We want the graph to experience what? Positive slope. Now, when we think about positive slope, we think about the graph is rising, but let's not think about the graph is rising. Let's think about the fact that it needs to be in this location. Okay, but it has to connect to this point. So what we're going to do is we're going to have the graph decrease to that point. Has to live above the x-axis, so that's where it's living. Now, this feels a little bit strange because you may be thinking to yourself, wait, this is a positive slope, so why is my derivative graph decreasing? Okay, I'll address that in a moment, but right now, just kind of go with it. Okay. All right, between -3 and -1, what slope are we experiencing? Negative slope. So where does my graph have to live? Below, okay, below the x-axis. Now, I see a point here, which means that my graph's going to be continuous, so it has to go through those points, and that helps me out, which means that my graph is going to be dipping below, but it has to go back up. It has to, yeah, go back up to that point. Okay, now you're maybe wondering, okay, how far down do I go? We're just going to have to know the graph will, it doesn't really matter. Okay, so right now it doesn't matter. We're just going to sketch our graph as smooth as possible. And we know that the graph will loop back up to -1 because we see a point there. All right, between -1 and 1, where do we want our graph to live? Above. Okay, so again, it's going to go up, come back down because there's a point there. And then to the right of 1, below. Okay, good. Okay. So the biggest issue that students experience with this is looking at this derivative graph and wondering, why is this decreasing when my slope, when my graph is actually showing increasing? Okay, so let me address this here. Remember, this is showing the slope value of the original graph. Okay, so let's talk about that for a moment here. Let's talk about just ballpark some slope values. We know the slope here is 0. If you just had to give me a number here, what can I say the slope at this point is? Some positive value, right? So maybe 3, okay? And what's going to happen as I get closer towards -3? What's my slope going to do? Decrease, right? It's becoming less steep. So maybe if this is 2, then 1, then 1/2. Okay. Okay, so let's look at these slope values here. What's happening to these slope values? It's what? decreasing, but it's all positive, right? But it's decreasing. So this 3, 2, 1, 1/2 is represented by this here. 3, 2, 1, 1/2. So this means that my graph has a positive slope, but the steepness is becoming more gradual. It's heading towards the slope 0. So this on the derivative graph is going to look like this on the original function graph. Does that make sense? All right. Yeah, it's going to take some time to kind of wrap our head around this, but we just have to understand that every location on this derivative graph is representing the slope value of the original graph, and that's why it looks so different. Okay, there's more to explore, but we'll come back to this. Now let's go back and let's talk about the concavity. Okay, so this graph, let's talk about concavity here. This graph is first experiencing what? Concave down. Okay, then it switches to concave up, and then switches back to concave down. Now, by looking at this graph, you're not going to know where the points of inflections are, but you do know there's a transition at some point in order for that to occur. We know how to find algebraically, right? We'll set the second derivative equal to 0, solve for x. But if you're looking at the graph, you're just kind of estimating. So let's say if I gave you the original graph, I would have to kind of tell you where the points of inflections are, especially if I don't give you a function to work off of. So for now, just to make it easy to find these points here, or to use points that are not decimals, I'm going to highlight this as a point of inflection, and I'll highlight this as a point of inflection. Okay, so concave down to concave up to concave down. Okay, so where are those points of inflections that I highlighted? -2 and what's the x value here? 0. Okay, so -2 and 0. Okay, so let's create a second derivative sign line here. And we're going to put that information onto our second derivative sign line. Okay, so we say -2 and 0 are our points of inflection. Okay. What is this graph doing initially? Concave down. Okay, so I'll represent that here. Between -2 and 0, concave up. Okay, and then to the right of 0, concave down. Okay. Now we're just going to rely on this second derivative sign line to create our second derivative graph. Okay, so here's my second derivative graph. Okay, so again, the y-axis is going to change in terms of what it represents. For the original function, the y-axis represents the position. For f prime, the y-axis represents the slope of the original graph. So what do you think the y-axis is not going to represent? Or the y value is not going to represent the what of the original graph? Not the position, not the slope, but the... What word do we use to describe second derivative? Concavity, yeah. So y-axis represents the concavity value of the original function. So what's our concavity value of the points of inflection? When f double prime is equal to what? Or how do we find points of inflection? Or how do we find critical points if I gave you the second derivative function? You would set the second derivative function equal to what? Equal to 0, right? So points of inflection has a concavity value of 0. Okay, so that's going to go on my x-axis. So points of inflection, -2 and 0. So anything above the x-axis will now represent where my original graph is going to experience what? Concave up. So I'm going to draw a notation, a symbol, label it to help me see it a little better here. I'll label it with that U to indicate concave up. Okay. Anything below the x-axis is where my original graph is going to be experiencing concave down. Okay, so I'm just relying on my second derivative sine line to help me build my my graph. Okay, so let's just figure out where it needs to live. Okay, so where do I want my graph to live? To the left of -2. Below, right? But it has to go through this point, so I'm going to make my graph rise to that point. Okay. I know it feels a little bit weird, right? Concave down doesn't look like concave down to us, but we're talking about so just think about the location, right? Okay, so you just match the label and just put where that graph is going to be, and then you know those points is going to help guide how the graph is going to move. Okay. All right, between -2 and 0, where do we want our graph to live? Above, right? But it has to loop back down because we see that there's a point there at 0, 0. And then to the right of 0, concave down, so below. We don't want to look at the shape of this graph, right? This shape is not going to represent what we experience to be concave up, concave down. In terms of the curvature, we got to look at the original graph, right? The original graph is what's representing those shapes, those curvatures that we're expecting. Okay, so what is a bit more challenging here is, you know, we'll do this on the second page, is what if I started you with the derivative graph, okay? Are we able to create a slope sine line? And then from there, from the slope sine line, can we create a picture of the original graph? So that's what's more important is on the AP exam, a lot of times they'll give you the derivative graph, and then you have to find information about the original graph based off the derivative graph. So let's just talk about that for a moment here. So if I start off with the derivative graph, what I want to do is I want to start with the x-intercepts. My x-intercepts are going to be the potential relative max and relative mins of the original graph. So my x-intercepts will go onto my slope sine line. And then I want to label my graph to be at either positive or negative slope. And I just look to see where my graph is located. If my graph is above the x-axis, I'm going to look at that label and I'm going to indicate that as a positive slope. Okay. Anything that's below the x-axis, I find my label, that's a negative slope. I will indicate that with a negative slope. Okay. Above the x-axis, positive slope. Below the x-axis, negative slope. And then once I create my slope sine line, then I'm just going to sketch a graph with the movements that I see here. I'm not going to rely on my derivative graph anymore. And I just want my graph to look like this. My graph may be in a different location, but as long as it has a relative max at -3, a relative min at -1, and relative max at 1, your graph could be anywhere as long as it has those behaviors. So that's what we're going to move towards to be able to get from a derivative graph up to a function graph. Okay. Likewise, we're going to have to be able to pull points of inflection, concave up, concave down information from the derivative graph. Okay. Now, what relationship do you see here between the points of inflection that we found here versus where they're located on the derivative graph? What's special about -2 and 0 in terms of their location on the derivative graph? Max and mins. Okay, let's talk about why that's the case. Okay, a point of inflection is where a transition occurs from concave up to concave down. Okay, something to kind of help us visualize it a little bit better is if you're on a roller coaster ride, then your points of inflection is going to be where you're going to be experiencing the largest steepness. Okay, where you're going to have that largest steepness, where you're going to feel like you're at the most kind of the angle part of your ride is going to be at these points of inflection. Okay, so the steepest part of your ride is going to be points of inflection. Okay, and that's why they're peaks and valleys, because these are slope values. So the highest and lowest slope values will be the points of inflection of your original graph. All right, and then second thing is we look at the slope of the derivative graph to find out the concavity of the original graph. So we define concave down as where the slope is becoming more positive. So wherever my derivative graph is negative slope, that's going to translate to concave down. Wherever my derivative graph is experiencing positive slope, that's concave up. Anywhere I have negative slope, it's going to be concave down. Okay, okay. So I'll revisit that after we go through another one of these examples. Okay, so let's look at example 2. Okay, example 2. Same process. We're going to create our slope sign line. And we're going to pick out the peaks and valleys and put them onto our slope sign line. All right, so where do you find the peaks and valleys in terms of the x values on the original graph? -2, where else? 0 and 2. Okay, so we're going to put those onto our slope sign line. All right, what slope are we experiencing here? Negative slope. Transitions to a positive slope. Back to a negative slope. And then transitions again, positive slope, okay? All right, let's create our slope sign line. Oh, sorry, create our slope graph. We can go ahead and put the -2, 0, and 2 where? On the x-axis. Yep, that's where my slope is 0, because now my y-axis represents slope values. So slope 0 is wherever my y is 0, which is on the x-axis. Let's go ahead and label so that we know exactly, so we can kind of just match up the symbols here. Anything above the x-axis is going to be where my graph is going to be where my original graph is experiencing positive slope. Anything below is negative slope. Okay, all right, so to the left of -2, where do I want my graph to live? Below, but it has to go up to this point, so my graph's going to look like it's rising. Between -2 and 0, above, but it has to loop back down, right? And these points kind of help us anchor where we want the graph to go. Okay? Between 0 and 2, down arrow needs to live down here. So let's just make the graph do that. And then to the right of 2. Okay. All right, let's talk about points of inflection. Let's say the points of inflection I gave you are at this point and this point. Okay, so concave up, concave down, concave up. Okay, so where are those points of inflection then? -1 and 1. Okay, so we'll go ahead and place them onto our second derivative. Sorry, these all should be g here. Second derivative sign line. We said -1 and 1. Okay, to the left of -1, what do we have here? Concave up. Between -1 and 1, concave down. And then to the right of 1, concave up. Okay, so we're just going to rely on this to help us with our second derivative graph. Okay, what can we put onto our x-axis? Yep, these are points of inflection, right? POIs goes directly on your x-axis. Let's go ahead and label what we're dealing with here. Second derivative, anything above is concave up. Anything below is where my original graph is going to be experiencing concave down. All right, where do we want our graph to live? Above, but it has to come down to this point, right? So okay, now between -1 and 1, concave down. So below, but it has to come back up to this point. To the right of 1. Okay, again, I want to draw the connection between the derivative graph and the point of inflection. If I ever want to find point of inflection, and I only gave you the derivative graph, you're going to be looking at the peaks and valleys, right? -1 and 1 are the points of inflection that we have here, right? And then concave up is wherever my graph is experiencing a positive slope. Okay, so concave up on the original graph is going to look like this on the derivative graph. Okay. Concave down on the original graph between -1 and 1 is going to be wherever there's negative slope. So if I ever want to figure out concave up, concave down on the derivative graph, let's look at the slope. Okay, so this is where concave up occurs, concave up occurs, concave down occurs. So concave up between up until -1, right? Concave down, negative slope is going to translate to concave down, and then positive slope on the derivative graph is going to translate to concave up. Okay. Now, I do want to draw a connection between what we know to be true in terms of power rule, and draw that connection between this. So look at the number of terms this graph has. Any idea what is the degree of this function, if you had to guess? X to the what? What degree is that? How about this, if I gave this to you here? X to the 4th, right? That's x to the 4th, okay? Okay, so let's say the function was x to the 4th, okay? Let's just deal with the highest degree, okay? X to the 4th. Maybe there's lower degrees here, but this is definitely x to the 4th graph. What's the derivative of x to the 4th? 4x cubed. Okay, what does a cubic graph look like? Like this, right? So we see that with power rule, it's also matching up with what we're creating with these graphs. Okay, what's the derivative of 4x cubed? 12x squared. 12x squared is a quadratic, and that's what we're seeing here with our graph that we created. Right? So what we know to be true from a power rule perspective, we're also seeing it matching up as we're creating our derivative graphs. Okay, so now let's look at this from a different perspective. What if we started off with a derivative graph and I asked you to create information about the original and the second derivative? That's what's more important. So let's talk about that on page 6. Okay, so now notice that we're now starting with a derivative graph. So what you see is not what you're expecting, okay? This is not relative max. That's not relative min. That's not relative max, at least not of the original graph, okay? We're going to try to gather information about the original graph, but notice that this is not the shape of the original graph. This is a derivative graph. Okay, so to help us remember what we're looking at, we're going to go ahead and just label the parts that are important. Okay, so anything on the x-axis is where my original graph is going to be experiencing slope 0. Anything above the x-axis is where my original graph is going to be experiencing positive slope. Anything below the x-axis is where my original graph is going to be experiencing negative slope. So we start off with our slope zeros, and we're going to create our slope sine line. Okay, so where are the slope zeros that we can go ahead and put onto our slope sine line? Negative. Okay, -4. Okay, where else? -4, -2, and 1. Okay, so let's go ahead and put those onto our slope sine line. Okay, don't look at the rise and fall of the graph. Look at the location and then match it up with the symbol that you see to the left. Okay, what's happening to the left of -4? Above or below? Below. I know it's rising, but it's below, and that below is going to match with the symbol for negative slope. So we're going to carry that negative slope over to our slope sign line. Yeah. Okay. What's happening between -4 and -2? Above. So above is translated to be a positive slope. Okay. Between -2 and 1? Below. So look at the symbol. Negative slope. Okay. And then to the right of 1? Below. So what? Negative slope. Now, we want to sketch a graph that has these behaviors in terms of the arrows. Okay, so don't look at this anymore. Your original graph is going to look nothing like your derivative graph. Okay, so f of x. Now, let's verbalize some of these things that we're going to expect. What do you expect at -4? Okay, at -4 though, what's happening? There's a what? Relative minimum, right? You see the graph rise, falling, followed by rising. What do you expect at -2? Relative max. How about at 1? Nothing, right? So the graph is going to fall. It's going to flatten out for a moment, wherever the graph is, and it's going to fall again. Okay. So it doesn't matter where your graph lives, as long as it has that behavior. So I'm just going to target some points. I'm going to make it kind of obvious in terms of the highs and lows of my graph. So it just, you can have your entire graph above the x-axis. You can have your entire graph below the x-axis. But for me, when I think of relative min, I think of a lower value. So I'm going to just pick a point that is relatively low. So I'll pick a point below the x-axis. You don't have to do this. As long as your shape looks like mine, that's good enough. And then -2, I want a relative max. So I'm going to kind of over-exaggerate it and just put a point that is high up. And then that 1, I know it's not going to be a relative max, relative min. I'll just pick a point somewhere where I can imagine myself flattening out, but then continue decreasing. Okay, so I'm going to connect these dots with these behaviors in mind. I want a relative min at -4, so I'm going to create that situation. Decreasing slope followed by increasing slope. At -2, I want a relative max. So increasing slope followed by decreasing slope. At 1, I want a slope 0, so I want my graph to flatten out for a moment, and it's going to continue decreasing. Okay, so now we're going to try to find information about the concavity based off of the derivative graph. Okay, so let's create our second derivative sign line. Okay, where do we find points of inflection if we're looking at the derivative graph? Peaks and valleys, good. So I'm going to highlight them. Peaks and valleys are going to be the points of inflection of the original graph. Okay, so where are those x values there? -3, -1, and 1. Okay, so -3, -1, and 1. Okay. Now, we don't want to look at the curvature here because this is not the original graph. So I don't want to say, oh, this is concave down, concave up, concave down. I'm looking at the slope. Okay. So wherever there's a positive slope, that's where I'm going to be experiencing concave up. So what's happening here? Positive slope, so therefore concave up. Positive slope, concave up. Okay. What's happening between -3 and -1? Negative slope, that's going to translate to concave down. Right. I know it doesn't look like it because this is not the original graph. Okay. How about between -1 and 1? Positive slope. So concave. Right. And then to the right of 1, negative slope, therefore concave down. And you may be looking at this and saying that doesn't make any sense because why is this concave up? Why is this concave down? Okay. But if everything is according to plan, then this curvature should match the original graph, right? So let me see if I can convince you of that. Okay. from up until -3, I should be experiencing concave up. So my original graph should resemble that, and it does. Right? Up until -3, that does look like concave up to me. Okay. Between -3 and -1, it changes to a concave down. Right? And that's consistent with the shape that we're experiencing. And then between -1 and 1, back to what? Concave up, or at least a portion of it. I mean, it is resembling concave up, not the full concave up, but it is concave up. And then it switches to concave down. So the curvature here matches the original graph, but we're pulling that a little differently from the derivative graph, right? Positive slope is going to translate to concave up. Negative slope of the F prime graph is going to translate to concave down. So filling out the rest of this chart is easy. Oh, sorry, one more thing. Let's sketch the derivative, second derivative graph, okay? Just based off of these symbols here. We know the points of inflection is going to live on the x-axis. We know above is concave up. We know below is concave down. So we'll place these points of inflection directly onto our x-axis. Okay, where do I want my graph to live? Above. So I want my graph to decrease to that point, right? Has to live above. Between -3 and -1, has to live below, goes down, but has to come back up. Between -1 and 1, above. And then to the right of 1. Okay. Now to fill out your characteristics, the only thing you have to rely on are these sign lines. Okay, because you're just going to tell me the x values of these intervals. Okay, so increasing, wherever there's an up arrow, that's increasing. Wherever there's a down arrow, that's decreasing. Relative max, relative min. We know there's relative min at -4. There's relative max at -2. Concave up, you have 2 intervals of concave up, 2 intervals of concave down, and then you have 3 points of inflection. Okay, we're not going to know how to find the y value of the relative max if I just give you the f prime graph until the second semester. Okay, so right now, if I only give you the derivative graph, the only thing you can tell me is the x value. We're not going to know the y value yet. Okay, let's see if we can make some progress for number 4. If we don't finish within the next 5 minutes, then we'll pick up tomorrow. Okay, so number 4, again, we're looking at the derivative graph. So keep in mind, this is not the shape of the original graph. So I don't want to just say, oh, that's relative min, that's relative max, that's relative min. It's not the original graph. So let's label so that we can know how to interpret it correctly here. So anytime I'm looking at the derivative graph, I like to just go ahead and make my label here. Slope 0 is the x-axis. Above is positive slope. Below is negative slope. So let's create our slope sign line. Okay, so what can I place onto my slope sign line? Yep, good. -2. Or else 1 and 3. Okay. don't get thrown off by the rise and fall of the graph. Look at the location, and then you're going to put either an up arrow or down arrow depending on where the graph lives. Okay, so this is your guide. This is how you're going to be filling out your slope sign line. Okay, so what's happening to the left of -2? Where is this located? Above, right? I know it's negative slope here, but that's because the slope is still positive, but it's becoming more heading towards 0. That's why it looks like that decreasing, but it's still in the location of positive slope. So you're going to just rely on these symbols. Okay. Okay. What's happening between -2 and 1? Still above, right? Still in this location. So you're just going to copy either one of these arrows, depending on where you are. Okay, and then between 1 and 3, below, so that's a down arrow. And then to the right of 3, positive, above. Okay, so now we're going to just sketch a graph with these behaviors. Okay, so whatever my graph looks like, I just want my graph to be rising, flattening out at -2, rising, relative max at 1, and relative min at 3. Okay, so your graph can be anywhere in terms of the y-axis, but as long as it has the same shape, that's what I'm looking for. So at -2, I'll just target a point. At 1, I want it to be just, for me, I want to over exaggerate it. So I'm going to put a point up really high because that's the relative max that I want to target. And then 3, I'm going to make it really low because I want that to be a relative min. Okay, so now I just want my graph to rise and fall with the same pattern as the arrows that I see. So I want the graph to rise to -2, flatten out for a moment, continue rising until it hits a relative max at 1, and then decreasing until it hits a relative min at 3, and then rises again.
You need to flatten it out for a second.
I did. I consider that as flattening out.
Do you need to though?
Yeah, you want to try to kind of, because -2 is slope 0, so it should look like slope 0 on the original graph. Okay, one last thing here. Let's just create a second derivative graph and we'll be done. Okay, so second derivative sign line. Okay, how do I pick out the points of inflection if I'm looking at the derivative graph? Peaks and valleys. Okay, so I'm going to highlight those points here. Tell me those x values. -2, 0, and what? 2. Okay. All right. Now I don't want to look at the curvature for concave up. I want to look at the slope. So what is this telling me here? Negative slope, so therefore concave down. Okay. Positive slope means concave up. Negative slope means concave down. Positive slope is concave up. This is the hardest part. The hardest part is filling out this concavity sign line based off the derivative graph. Okay. Once you can get these two slope sign lines, concavity sign lines, everything else is easy, okay, or easier. Okay, good job. No homework tonight. We'll finish this up and we'll talk about optimization. Okay, come on, Ben, get your phones.